Inference on the mean of a population. Variance, no. So there is unknown mean. Mean is unknown, but the variance is known. In this case, what do? We write a hypothesis. We do an hypothesis testing. And for testing, we first write the null hypothesis, which is mu is equal to mu 0. And the alternative hypothesis, mu is not equal to mu 0. And for the z value calculation, we have the formula for that. Z0 is equal to x bar minus mu 0 all over sigma square root of n. So that's the equation we should be memorizing. We will calculate the values with this formula, and let's write it. If z, the absolute value of what we find, is greater than z alpha over 2, where z alpha over 2 is the upper limit. This procedure is sometimes called one sample z-test. So we take one sample, and according to that one sample, we give a decision with the hypothesis testing. So let's apply this knowledge to example 4.1. Example 4.1. It says that the response time of a distributed computer system is an important quality characteristic. The system manager wants to know whether the mean response time to a specific type of command exceeds 75 milliseconds. From previous experience, he knows that the standard deviation of a response time is 8 milliseconds. Use a type 1 error of alpha equals 0.05. So what do we have as the values? For example, we can write the hypothesis as null hypothesis. Mu is equal to 75, and the alternative one is, since it says command exceeds 75, then mu is greater than 75 we should write. What is the difference between writing greater than and equal to? Do we take one side of the graph or the both sides? We will decide on the question. So for this one, we will take only one side, which means that since it says exceeds, for this part, we would like to find the z value for 0.05 from the table. And plus, it gives information about the sample number, and it says sample number is 25. And the average x bar is equal to 79.25 milliseconds. Okay, so we need to calculate the z value. Let's write ZO is equal to x bar minus mu O all over sigma over square root of n. Let's put the values in places. 79.25 minus 75 all over sigma is, we didn't write sigma, it was 8. So 8 over square root of 25, which is 79.25 minus 75 times 5 all over 8, and that's equal to 2.66 for the z value, for the z now. And we need to find the z value for 0.05. We need to look at our table. So 0.05 is on the right. So this part, let's shade the other part. We want to look at the table for the green area, which will be 0.95. So in the class we found that 0.95 was 1.6. So this values the probability of z 0.05, z is greater than that, is equal to, no, we are finding the z value, sorry. So the z value is 1.645. We will compare what we have found with the calculation with our alpha value. Now let's draw it again to understand what we found as an example, as a solution. The alpha value was given to us. It was 0.05. So this z value was 0.05 was 1.645, and what we have calculated is 2.66, which is far from this. Maybe it is somewhere like this. ZO is equal to 2.66. So we found this by calculating, and it is far away actually from the mu equals 75 value, what we have found. Where did we find this? We found this with the average 79.25. And we say that since it is in the shaded part of the alpha value, we need to reject the null hypothesis. We need to reject this. Somehow the average may be moved to the right, so that what we took as a sample and what we found as a average is so far away from our previous average. So we say that this value is less likely to come from the normal distributed with the average 75. So we reject the null hypothesis. The null hypothesis says the population average is equal to 75. Now, in this situation, we were checking. We didn't know the population average. This was unknown. We thought it was 75, but with our hypothesis, we found that it is less likely to be equal to 75. So it should be greater than 75. We reject the null hypothesis. We say that it is not 75. It should be more than that. That's our conclusion for this example.